Hello everyone, this is Sanket Thakur, and today I'll be presenting my work on guided attention for next active object for short-term anticipation. This work was done in collaboration with Italian Institute of Technology, University of Genova, University of Verona, and University of Trento. And before we talk about next active object, it is important to know what are active objects. Now, in a work which was done a while ago, it was said that an object which is currently in contact with human hands or we currently use for some interaction are called as active object. In this case, you can say the knife and the onion are called active objects, whereas the other objects such as the pan, the bowl, and the other things are called as passive objects. Now put this into context of action anticipation, the next active objects will be those objects which will be used in future action. Now, the question is, can we detect a next active object when given a single image? For this particular given image, it is also very difficult for a person to identify which object will the person use to carry out future action. But if we replace this image with a certain video clip describing the past interaction with the objects of the person, then it's relatively easier for a model, for a person as well, to identify which object the person will interact with in a given near future, which basically comes to defining the short-term anticipation task. Now, this task was first coined in a paper which was published in CVPR 2022 called Eco40 paper. And they say that for a given video clip, which is called as observed segment, we extract the last observed frame from that particular observed segment, and we have to determine the location of the next active object and also the class for that particular object. In this context, the green bounding boxes depicts the location of what object will be used in future action, and the classes. In addition to this, the model has to identify two more things. First is what will be the future action that will be done by the person, and also that time to contact, how much time will it take for the person to touch or make an interaction with that particular object. Now, in a crux, short-term anticipation has four unknowns. Very first is the bounding boxes, that is the spatial location of the object and the last observed frame, and also the class for that particular next active object. In addition, we also have to identify the future verb, that is the future interaction taking place, and also the time to contact, that is at what time in the future will the interaction begin with that particular object being identified. Now, for our model, we like to assume that if we can also identify certain number of object detections in the observed segment, we will be able to better identify the next active object. Because remember, we also have to identify the location and also the class of the next active object. So the idea is if we can also extract object detections from any object detector, giving the location and also the class of the objects detected in the observed segment, the assumption is it can help us identifying the next active object relatively better as compared to not using those object detections. Which brings us to the formulation of our model. Now, in the very first stage, we use a object segment or a video clip, and from that video clip, we extract a certain number of frames, or we can call it a sample number of frames, because we cannot use the entire video clip. So we sample a fixed set of frames from that particular video clip. Now, from those RGB frames, we feed them to an object detector. Basically gives us the object detections for all the objects being detected in the corresponding number of sample frames. Once we have these two, we use the feature extractor. In our case, we're using a 3D CNN on ResNet 50, and then we extract the patch features from those RGB frames. In addition, we will use an NLP-based model to extract the object embeddings from the object detections which we have. Now, we use these two things to formulate our object detection, object guided attention based module. We use the patch features as the query, and we use the object embeddings as the key and value pair to extract the attended patch features from our object guided attention module. Now, in further detail, object guided attention module is basically inspired from the multi-head attention based setup from Attention is All You Need paper. As I said, the query is formulated from the patch features given n number of frames, and key and value pairs are the object embeddings for a fixed set of n embeddings per frame. So what we have is we fix the number of detection which we can use from a single frame. For a specific frame, if we have less number of detection identified for that frame, we append additional dummy detections to that to make the value as m, because m is our the number for fixed detections. We add dummy values of object detections of size is 0 to make it a complete length, and then we use multi-head guided attention. We use the multi-head guided attention module to extract the attended patch features from the object guided attention based module we have. So this comprises for the part 1 of our model. In part 2, we use a high resolution last observed frame. Why we use that? Because we need to regress the location of the next active object in the last observed frame, which is the reason we use a high resolution last observed frame. And then we feed them to a 2D CNN based book to extract the 2D feature maps for that. Now, when we combine them together, we are basically combining the 2D feature stack. So the 2D CNN gives us feature stack from the high resolution frame, and the attended feature maps and the attended features also have their own feature levels, which we have. And we combine them together using a combined feature parameter, which basically combines corresponding feature maps we have for the 2D CNN and also the 3D CNN, the attended patch features we have. In the end, the output of this combined feature parameter is being sent to a prediction head, which is inspired from the Detectron2 based head, which gives us the location and also the class of the next active object in the last observed frame, and also the future verb and the time to contact in our scenario. Again, if I want to repeat this, we have a video clip as the observed segment. We extract n sample frame from that. We use an object detector to extract the object detections from those sample frames. We use a 3D backbone to extract the patch features from the sample frames, and also the object embeddings from a different MLP base layers. Now we then feed these together to an object guided attention based module to get the attended patch features. In parallel, we have the high resolution last observed frame. We feed them to a 2D CNN based backbone to extract the 2D feature maps. Now these two feature parameters are combined together in a combined feature parameter network, and the outputs are being sent to a Detectron2 based prediction head, which gives us the 4 unknowns for the short anticipation task which we have. Now, talking about evaluation, now based on the evaluation metrics provided by the EGO40 paper, it says that for a predicted ground truth bounding boxes and for a predicted bounding box and the ground truth bounding box, the intersection of a union has to be more than 0.5. So a predicted box will be considered as a true positive, and the intersection of a union is more than 0.5. Which basically comes to the evaluation. We are using a top K evaluation for different metrics. Now, you need to be careful that for all these 3 different metrics, the box has to be a true positive. That is, the predicted box has to be a correct prediction. That is, their IU has to be more than 0.5. We do the evaluation on noun top 5 MEP, mean average precision. We use the evaluation on noun plus verb, noun plus TTC, and the overall, that is noun plus verb plus TTC, and also the box, of course. Also, one more thing, that for a TTC to be accurate, the absolute difference between the predicted TTC and the granted TTC has to be less than or equal to 0.25. For example, if the ground truth TTC value is 1 second, the range within which our model can predict to be a true positive is 0.75 seconds to 1.25 seconds, because the absolute difference for these two values will be less than or equal to 0.25 seconds. Now, talking about some of the evaluations which we did on EGO40 datasets. Again, EGO40 dataset is the largest EGO40 is the largest egocentric dataset which was released by Facebook last year at CVPR 2022. Now we noticed that our model is performing best on the validation and the test set. Also, one thing to consider that this work won the CVPR 2023 challenge on EGO40 short anticipation task for the test set of this particular dataset. We noticed that we are performing better on most of the evaluation metrics, that is noun top 5 MEP, noun plus verb, noun plus TTC, and also the overall. You can also notice that the overall accuracy is still very low, which can be understandable because this is a very challenging task because we are predicting 4 unknowns altogether, which basically also leads that there is a lot of scope of improvement. There's a lot of research has to be done, which can be done in this particular task. And also talking about some of the qualitative results, one thing to note is that for the Detectron 2 based prediction head, the number of objects that are being detected is 100. We use the NMS threshold for post-processing. We set the NMS threshold value to 0.6 to reduce the number of objects being predicted by our model. In a nutshell, the number of predictions which we can have for a particular given clip are about 3 and 4. So you can see for different number of clips, on the last observed segment, most of the predictions are located or confined to a single object where the confidence of the predictions are relatively high. Which brings me to the end of my presentations, and I would like to thank you for your attention. Thank you again.